You're listening to Let's Talk Creation with Todd Wood and Paul Garner, the creation show where we learn, grow, and worship.
Well, it's great to be back for another episode of Let's Talk Creation with Paul Garner and Todd Wood. I'm Paul Garner.
And I'm Todd Wood.
Don't forget to subscribe, hit that subscribe button, share our episodes with your friends, tell your friends about us, and leave us a positive review. All of that is very, very helpful to us as we seek to grow our audience. We're really pleased to see, some of the reaction that our recent episodes has been getting. And we love to hear your comments, your feedback, your questions. So do keep sending all of those to us.
That's right. Even if you want to call us a ding dong or whatever.
Yeah, even if you do. It's great to have you here. Last episode, Todd, you will remember that we began a very deep dive into the science of comets. We learned all kinds of interesting things about comets. We learned that they're small icy objects that orbit around the sun in very highly elliptical orbits that sort of bring them periodically close into the inner solar system. We talked about how comets have been understood through history, and what we know about their structure and composition. So I think that gives us a good platform then to move on to what we want to talk about in this episode, which is where comets come from and what they can tell us about the origin and age of our solar system. This is a question that has been discussed at great length in both the secular literature and in the creationist literature. And to help us to dig deep into this subject, we have an expert in astronomy, Dr. Bob Hill, joining us once again. Bob, it's really good to have you here again.
Glad to be back.
Todd and I are not astronomers of any kind, and so we are particularly glad to have you here. Bob, for those who don't know, has a PhD in astronomy. He's a member of the American Astronomical Society. He's a professor, associate professor at Bob Jones University. I think that's right. Bob, is that correct? And Bob is also president of the Creation Research Society. We will put links to the Creation Research Society in the show notes so people can check that out. And last episode, we mentioned the CRS's summer conference in 2025. That summer conference is going to be held in St. Louis. And so do consider going along and checking that out. So we will put links to all of that in our show notes. Bob, we had a great discussion last time, thinking about the science of comets. And I just wonder whether we could begin just by briefly reminding our viewers of some of the things that we said last time, in particular about the two main types of comets, because I think that's going to be important in our discussion today. So just refresh our memories about that, please.
Okay, so they have what they call short period comets and long period comets.
Yeah.
Short period comets have orbital periods of, say, 200 years or less. Long period comets have orbital periods greater than around 200 years. Short period comets orbit the sun in pretty much the same plane as the Earth. There's a tilt there, but not dramatic. While long period comets, their orbital tilts can be dramatically different than the plane of the Earth. Short period comets orbit the same direction as the planets, what we call prograde. Long period comets can go either prograde or the other way, retrograde.
Yeah. So those are the main differences. So we really distinguish these two sort of classes of comets on the basis of their orbital characteristics, their orbital dynamics. Yeah. And that's going to be important, as I say, as we come to this discussion about where do comets come from. We also said sort of briefly in the last episode that comets are regarded as primordial objects. In other words, they're thought to have originated at the same time as the solar system itself. But as we're going to see in this episode, comets seem to have a maximum lifetime that is substantially less than the conventionally accepted age of the solar system, which is 4.6 billion years or thereabouts. And so, creationists have often appealed to comets as evidence of a recent creation, a young solar system. And I just wonder, how far can we trace that creationist argument back? When does it first appear in the creationist literature, do you know?
First, let me explain why we've got the argument. Every time a comet comes around the sun, it loses some of the ices in the nucleus. That makes the tail. So the mass of the comet drops every time it comes around.
Yeah.
Well, it's only got so much ice. It goes around so many times, it should eventually have no ice to make a tail.
Yeah.
Yeah.
And you start running, estimates and numbers, and any short period comet that was primordial should have lost all its ice by now.
Yeah.
So why do we still have short period comets if the solar system is really 4.6 billion years old?
Yeah. So that's kind of the essence of the argument. So, yeah. So when does that argument start being used, in the creationist literature?
It goes back pretty far. Whitcomb Morris mentioned this in the book The Genesis Flood in 1961.
Wow.
That's pretty much the beginning of the modern creation.
Yeah.
Harold Slusher, when he was with the Institute for Creation Research, wrote about this as well. Danny Falker's written about it. It's kind of been a continuous topic and being pretty much unchanged.
Yeah.
Since Morris and Wickham.
Yeah. Yeah. So this is an argument that's been around quite some time. And so, hopefully in this episode, we can sort of take a detailed look at this argument, try and break it down, and also think about some of the possible counter responses, that have been raised and some of the new developments in this argument in recent years. Perhaps we could begin just by thinking about the loss and destruction of comets. Now, you've already mentioned briefly this sort of gradual loss of mass because of the vaporization of material or the sublimation of material from the comet. But there are other ways too, aren't there, that comets can be lost from the solar system, more sort of what we might say catastrophic ways. Just mention some of those, Bob, if you will.
One of them is they can actually be ejected from the solar system. For example, comet A117 UUD in 2024 got too near some of the larger planets. I think this one was Saturn. An gravitation interaction with Saturn tweaked its orbit and flung it out.
Wow.
They can be ejected.
Wow.
And also, it could hit something else.
Yeah.
For Comet Shoemaker-Levy 9, was famous one was July 1994. When it went around the sun, like the previous time, it got close. Tidal forces of the sun tore up the nucleus. And so when it came back around, Jupiter was able to tweak its orbit some too. And these comet fry was smacking Jupiter in the multiple impacts, releasing more energy than if we set off all the nuclear weapons on her.
Wow. I remember that happening. I remember, in the science news, the spectacular photos of that object kind of breaking up and then, colliding with Jupiter.
Our understanding of Jupiter, because these things smack Jupiter so hard, you could peer down, you can figure out what's below the surface.
Yeah, wow. That's amazing. Was that something that amateur astronomers could see? Could you see it through a telescope from your backyard, or was that something that you had to have a more powerful telescope to see? Do you know?
If you really knew what you're doing, you got a nice size scope. Like a serious amateur astronomer, maybe.
Yeah. Yeah.
Because the pictures we see are from Hubble and stuff.
Yeah, sure.
Or Keck, or one of the big major ones.
Yeah. Okay, so we've got comets that can be ejected, comets that collide with other objects, and I guess gravitation gravitational forces can just rip these things apart? Is that
tidal
something
forces,
else that happens?
they get too close. They can tweak their orbits.
Yeah. Yeah.
So when you say tidal force, are you talking about the kind of gravitational pull that the moon uses to create tides? Is that where that's coming from? Tidal force?
Yes. For example, if the sun's over here,
Mm-hmm.
and here's a comet nucleus, force of gravity on this side is stronger than the force of gravity on this side.
Sure.
That's tidal force.
Okay.
And it tends to stretch objects.
Yeah.
And
so if it's solid rock, it can hold itself together better.
Yeah, but if it's got a lot of melting ice stuff, then you could
it might be able to
pull it apart. Wow.
Pull it apart. Yeah.
Crazy.
Yeah. And the these gravitational forces, as you say, they can sort of alter cometary orbits. And that happened in the case of the new comet, which many of us were observing back in mid-October. Yeah. Which is incredible. I mean, just mention that again, because you told me about that, and that seems incredible to me.
Yes, they had something like 1,000 data points of observations on its way in. So they can pin down its orbit pretty precise. They do the curve fitting. And then they did the same thing on its way back out. And its orbital period changed by millions of years.
Wow.
Gravitational interactions in the solar system.
Yeah. Yeah, this is just incredible. So there are these sort of catastrophic ways that comets can be lost. But then there's also this gradual sort of loss of mass that you mentioned. As the comet comes close to the sun and it begins to warm up, it begins to lose mass. Just remind us exactly how that happens again, Bob.
Yeah, so remember you got the comet nucleus, which is rock with ices.
Yeah.
And when a comet comes in there, say around the orbit of Mars, the sun starts heating it up, and those ices sublimate, going straight from a solid to a gas, and then that gets left behind. Yeah. Either sunlight pushes away the dust, or the solar wind pushes away the gas particles. And the solar wind is especially pushing the gas particles from the ices.
Yeah.
So the mass of ice attached to the comet decreases every orbit. And so they're estimating, every time it goes around, it loses maybe 0.1% of its mass to 1% of its mass. Just from sublimating that ice. Well, it only has so much ice.
Right. Yeah. So how big is a typical comet nucleus? I mean, what is the mass of let's try and sort of break this argument down. How much material are we talking about in the comet nucleus to begin with?
Okay, a typical comet nucleus is, 5-10 miles across, roughly that rate.
Yeah.
Many of them are less than that. That's a nice ballpark. And so let's go with 10 kilometers across. A reasonable mass, say around 5 times 10 to the 14 kilograms. Figure the rock and stuff. That's pretty reasonable. And so when they measure the mass loss for Comet Halley, that was 54 tons of gas per second it was losing.
Wow.
So, yeah, the closest approach to the sun, like Mars, comes near Mars orbit, exits Mars orbit, like maybe a third of the orbit. That means during that one orbit is losing a total of 5.7 times 10 to the 11 kilograms in one passage.
Yeah.
And so with these rough numbers, if it has an orbital period of 200 years, being an actual comet, it would run out of ice like 95 times around.
Yeah. Wow.
Now, most of the time, I think I've seen like 40 to 50.
Yeah. Yeah. So 40 to 50 passages around the sun. Yeah, orbits. And just so that our viewers didn't miss that, you said that the peak mass loss rate for Comet Halley is measured at 54 tons per second. Is that right? As it comes close to the sun. I mean, that's an incredible rate of loss of material from the comet nucleus. That's incredible. So we can understand then why these things have a kind of limited lifetime, a limited lifespan.
The Halley's Comet must have been huge. It must be huge. Do we have a size estimate on that thing, Halley's Comet?
I've wondered about that one in particular, because we've known about that. You can trace that back to like Sumerian times.
Yeah.
Yeah.
How big was it then? I don't know. or does the mass loss vary?
Yeah.
We're just doing a ballpark calculation right now.
And of course, for much of its orbit, when it's further away from the sun, obviously the mass loss rate would be much less. But
it'd be zero.
It'd be zero. So we're talking about when it comes close to the sun, that's when you're losing most of the material.
Yes.
Yeah.
No, in a biblical time frame, for our ballpark calculations, the comet would have gone around the sun 30 times.
Okay.
In 6,000 years or so.
Okay.
So no problem for us.
Yeah.
However, if the solar system is 4.6 billion years, it would have made like 25 million passages around the sun. It should be a burnout rock.
Right.
Yeah.
Right.
Yeah.
So that basically sums up the problem with short period comets. That they have orbits of 200 years or less, and with that kind of loss rate as they pass close to the sun, they can only survive a relatively small number of passes. And 25 million passages around the sun, we shouldn't have any short period comets left.
It should be an asteroid now.
Yeah, it should be an asteroid, right? What about long period comets? Because obviously they've got much longer orbital periods. So what can we say about the lifetime of longer period comets?
Depends which ones we're talking about, because you're talking like 200 to 500 years.
Yeah.
It can last so long, but if it's got like an orbital period like 10,000 years, you get another how long they can last. And you still have something similar. Like maybe 95 to 100 passages, you're going to have trouble. And you do run into a maximum here for the orbital period. It's called the Hill radius. Not related to me, unfortunately.
Too bad.
There's like a Hill radius. It's like 235,000 AUs from the sun.
Now, when you say AU, yeah, so that's the Sun-Earth distance is one AU, one astronomical unit. Yeah.
Yeah. At the Hill radius, basically gravity is so weak from the sun, it's considered like a boundary. It's not attached to the sun.
Yeah. Yeah.
Now that's just that's just a rough number there. They need something.
Yeah.
Sun's gravity goes out for it.
But the point being that there is a kind of maximum orbital period that a long period comet can have.
Yeah, so like 11 million years or so.
Yeah, yeah. And so that still leaves a problem in terms of, this mass loss rate. Even though they're not returning to the inner solar system as often as short period comets. Over the lifetime of the solar system, we still have something of a problem there. So this is the basic argument then, that creationists have made, that comets appear to have maximum lifespans which are much less than the conventional age of the solar system, even though these are thought to be primordial objects that date from the time of the origin of the solar system. So hopefully, our viewers can kind of see the paradox here, the problem here. And I think I'm right in saying, that this problem has been recognized for a long time. It's not like evolutionists are not aware of this problem. They've known about this issue for a very long time, haven't they? Long before creationists talked about it.
Not stupid.
Yeah.
They noticed this early on.
Yeah.
And so if you're already convinced the solar system is billions of years old, short period comets only last thousands of years,
yeah,
there must be another source of short period comets.
Yeah.
It just follows.
Yeah.
Yeah. Yeah. So
and the main suggestion has been the Oort Cloud.
Yes, I was going to say, so let's talk about the different solutions to this problem that have been proposed. And so the Oort Cloud, I think, was proposed as a source of long-period comets. Is that correct?
Yes. Jan Hendrik Oort, 1950. Basically, as the solar system formed, you got this huge amount of small comet nuclei, thousands of AUs from the sun. These are just leftovers from the formation of the solar system.
Yeah.
And they're extremely long orbits. Most of them are kind of circular, in fact, what they're thinking.
Yeah.
And then something perturbs that.
Yeah.
Making new long period comets.
Yeah. So this Oort cloud is envisaged to be not a disk. It's a kind of spherical shell of comets.
Spherical shape. Mm-hmm.
Yeah, at very great distances from the sun. So in effect, these comet nuclei are kind of in deep freeze. They're sort of in suspended animation at very great distances. Yeah.
They were talking 3,000, 100,000 AUs from the sun.
Yeah. But every now and then something happens to sort of disturb this cloud, and some of these objects
within the cloud itself.
Yeah.
Or we pass by, some star gets a little close, the gravity tweaks it.
Yeah. Yeah. And so I'm trying to make the connection here. So how then do people connect these Oort cloud objects with long period comets? What is it about long period comets that is thought to then be explained by this sort of Oort cloud idea?
Well, you have all these long period comets that come in from any direction. They can be prograde or retrograde. They're more random than the short period comet.
Yeah.
In that aspect.
Yeah. So the direction is because the Oort cloud is thought to be spherical, so they can come in from any direction. Mm-hmm. And their orbits are just sort of more random. So it can so it's thought to explain the origin of these long period comets. Now, can the Oort cloud explain short period comets? Because they have rather different orbital characteristics, right? So
the original idea of the Oort cloud was one of these long period comets. When it comes in, it gets too close to like Jupiter or Saturn, and that's enough to tweak its orbit to a short period comet.
Okay. Does that work?
I think it does. If you treat the like Jupiter Saturn as an extended object, not as a point,
mm-hmm.
and you have moons and stuff, I think that's conceivably at least plausible.
It would have to be, but it would have to be then a long period comet that happened to be in the ecliptic plane and happened to be prograde
or passing through the ecliptic plane.
Okay.
And it got near Jupiter or Saturn, and it tweaked its orbit.
And would that mechanism be efficient enough to kind of explain the number of short period comets that we see? Is that gonna work for the numbers of comets that we observe?
That's a good question there. Okay, before we do that, I got a story.
Okay.
When I was in grad school, I helped out at the planetarium there at Ball State University. And so I gave shows, and occasionally I have to answer questions. So I asked the planetarium director, who was an astronomer, and I was very careful. I hid my cards carefully. So it's like, so if somebody asked me a question, what's really the best evidence for the existence of the Oort cloud? What should I say? And he had a puzzled look for a second, and then, well, I suppose the best evidence for the existence of the Oort clouds, we still have short period comets. What did he do?
Yeah.
Yeah.
He's so convinced of his paradigm, he couldn't imagine anything else.
Yeah. We're coming back to this question of efficiency. Is that sort of that transformative effect of gravitational interactions turning long period comets into short period comets over the lifetime of our solar system? Is that going to produce enough short period comets? I guess that's my question.
Now, that's an interesting one because I was talking with Dr. Danny Faulkner, Answers in Genesis, over the phone, and I just got the paper he wrote on this topic.
Mm-hmm.
The orbital period of the Shushanshan, trying to pronounce that correctly, the one that was in October, changed so dramatically, and it's some of the major axes way out there, like 79, really close to that hill radius I was telling you. You start running numbers off that kind of stuff. They start to think these interactions are more often than they're expecting. And you start running some basic numbers. And it's like, you're out there where the gravity of the sun is so weak and you get these perturbations more often than they're expecting. Would the Oort cloud actually last billions of years? That's an interesting question.
That's a different way to think about it. Yeah.
And so, he's suggesting we need more astronomers or creationists. But he's someone who could do computational astrophysics of the orbital stuff and play around with it. Just how long will the Oort cloud really last? The kind of interactions we're thinking of now. Because if the Oort cloud can't last long enough, this is a moot point.
Yeah.
But it seems
and presumably objects could be lost from the Oort cloud into space as well. I mean, not into the inner solar system, but just lost to interstellar space.
Yeah.
But it seems to me, I mean, going back to your anecdote about the astronomer you were asking at the planetarium, I mean, if you're talking about tiny little objects hundreds of thousands of AUs away, this is not something that we have direct observational evidence of. Is that right? We have not observed directly the Oort cloud.
Right. We observe objects that when they go out that far, get into the Oort cloud.
Okay.
But actually observe the Oort cloud, no, we have not.
Okay. So in terms of then of could that explain comets, I guess you could just hand wave and say, well, the Oort cloud must have a lot of things in it then. I mean, that would be my expected reaction.
That's the kind of stuff they end up doing. Is they have they're so small, you can't see them. You can do the calculations. Well, I'm just going to maintain this kind of rate of putting in comets. They've got to have at least this many out there.
Right.
Yeah.
Or this density.
Yeah.
But I would guess then you would end up having to have a density so thick that it's impossible to imagine you wouldn't observe it. I mean, I suppose that's possible. I don't know. I'm not an astronomer, but
running numbers. Distances between things can still be enormous.
Yeah, I suppose that's true.
Yeah, just imagine the average person's idea of the asteroid belt. They get that from The Empire Strikes Back, right?
Nice.
The average distance between one asteroid in the asteroid belt to another asteroid in the asteroid belt is like 1 million miles.
Oh, that's
okay. Wow.
that's not.
It will be even bigger at those distances for comet nuclei.
Okay.
Yeah.
So you could totally fly the Millennium Falcon through the real asteroid belt, no problem.
Yes.
Okay. Well, now you heard it here first,
that
folks.
That wouldn't be as cool.
So we don't have direct observational evidence for the Oort cloud. Now, that obviously doesn't mean necessarily it doesn't exist.
Right.
It's inferred from the orbital dynamics of long period comets, basically. Right. So these things have orbits that would take them out into the vicinity of where we think the Oort cloud is. But we don't have direct observation because these things are just too small and too far away, so we can't see them. But Yeah, so it doesn't mean it doesn't exist, but it does kind of mean that there is a level of uncertainty here that we need to be aware of. You know, we are talking about something that is in the realms of a hypothesis to explain the origin of these comets.
Mm-hmm.
Okay, so that's the Oort Cloud. I wonder if we could just come on now to talk about this thing that I've heard of called the Edgeworth Kuiper Belt, because this is, as I understand it, what most astronomers today think is the source of the short period comets. They actually think they're coming from this much closer cluster of objects, and these things are in the plane of the solar system, right?
Yes.
So they have orbital characteristics much more similar to those of short period comets.
Yes.
So tell us about that.
I like calling them trans-Neptunian objects.
Okay.
Objects farther out than Neptune.
Yeah.
I think it's a better description, actually. And we are finding stuff there.
Yeah.
We're finding icy bodies out in that range. So at least that sounds plausible. And then you need something to perturb these nearly circular orbits into a more elliptical orbit.
Yeah. And are there plausible mechanisms to do that? Have we even observed it happen?
I'm not sure we've observed it happen. Maybe a close interaction with a long period comet as it came through, because the gravity of gas giants is getting weak out there. You might get some kind of a resonance with orbital periods of the big planets that could tweak that, but I'm not too certain about that.
Yeah. So basically, this idea of the Kuiper Belt, or as you know, the trans-Neptunian objects, is that beyond the orbit of Neptune, there is this kind of disk of icy objects.
Yes.
Since the mid-90s, we have been able to image many of these objects, so we know they're there.
We know
this
they're
is not
there.
like,
The ones they found that I know of are tend to be bigger than comet nuclei.
Yeah.
Okay. Yeah. Does that mean that they can't be the source of comet nuclei because they're too big, or does it just mean that we haven't been able to observe the smaller ones yet?
We might not be able to see the smaller ones.
Yeah.
Or
So
maybe
again,
these things collide with something and break.
So it could be an observational bias again, that we just, we see the big things first because they're easier to see.
Easier to see.
Yeah. Pluto. Now, Pluto, is Pluto a member of this sort of collection of objects, these trans-Neptunian objects? Because it kind of got demoted, didn't it, as a planet?
Well, reclassified is a better term.
Reclassified. Yeah.
So what was the motivation there? Is it because there was so many other things being found in its orbit?
There's multiple things. Originally thought Pluto was bigger than it is.
Okay.
I thought it was bigger than it is. Then in the 80s, they found that it had a moon and would like eclipse Pluto. They do that off and on. They could time that. But looking at the brightness changes of Pluto, you can figure out the sizes of each. And Pluto is a lot smaller than they thought. So that was like the beginning. Also, we start looking at planet characteristics like eccentricity. They naturally group together. You've got the terrestrial planets and the Jovian planets. And then Pluto was always weird. No matter what characteristic of planets you're looking at, they clustered nicely for the inner solar system.
Pluto was weird.
Jovians, and then Pluto was weird. It had the biggest. Pluto has a much bigger eccentricity to its orbit than the other planets. Much bigger. Its tilt of its orbit to the Earth's ecliptic is much bigger. So just a bunch of stuff just didn't seem to work right. And then they kept finding stuff out in that range of Pluto, and a bunch of those were round.
Oh, okay.
And so, do we make little kids memorize like 60 names for planets? Because there was no good definition of planet at that time. I mean, you think about it. Before, it was just intuitive.
Yeah.
Yeah.
You know, it's like I do this in my class. I show pictures of cars, trucks, and vans. And they just right away know what each of those are. Then I show them a picture of an old El Camino. What's that?
It's an abomination.
Yes. It didn't last long for obvious reasons. Is that a truck car or what? And so before we have this intuitive approach to planets, Pluto and these other things, we need a better definition. So the official naming organization by treaty, the international treaty is International Astronomical Union. And so they had proposals how to define planet, what to do about Pluto. And so I remember I was working with my doctor at the time. They had a big meeting, the IAU went late in the evening and they voted. New definition of planet, Pluto was reclassified.
Very interesting. So we've got this sort of body of objects in the plane of the solar system, roughly speaking, out beyond the orbit of Neptune. Now, have I got this right? Is that collection of objects, these TNOs, is that thought to be the source of the Jupiter family short period comets that we talked about, and then the Halley type short period comets are thought to come from the Oort Cloud, or is that too simplistic?
I'm not exactly sure, because I could easily see starting out as like a Halley type and get tweaked to the Jupiter type as based on interactions from your solar system and stuff.
Okay. And are there enough objects in beyond the orbit of Neptune again to supply the comet population for very long periods of time? I mean, that would be a crucial question. How many objects are there actually out?
I'm not sure about the numbers, but I think they would say something like, well, you've got the Oort Cloud. Some of those come in close. They get tweaked into the Kuiper Belt, and then something tweaks them on in. So it's like a parking lot or something.
Yeah. Yeah. So the Kuiper Belt is being replenished in effect by the Oort Cloud.
I think that's what they would say.
But what would do that? I mean, what would move something into the Kuiper Belt? There would have to be something there, or am I wrong?
Well, if you have a long period comet from the Oort Cloud, it gets close enough to one of these Kuiper Belt objects. Some of those are good size.
Okay.
Maybe the grav from them, between two or three of those, could tweak the orbit.
Yeah.
So all you'd need to do is start out with something out there as a trans-Neptunian object in orbit that could start.
Or a few of them anyway.
Yeah, a few of them. Sure. Okay.
So this discovery of these trans-Neptunian objects and this idea, those have been observed since about the mid-90s, so we kind of know they're there. And then you've got this idea of the Oort Cloud, which was first proposed in 1950. These ideas somewhat complicate the argument concerning the age of the comets, because these are being proposed as plausible sources for new comets to come into the inner solar system, in effect replenishing the supply of comets that we're observing. So they're being kept in some kind of suspended animation at great distances, but occasionally sort of being perturbed and coming into the solar system and becoming new long period or short period comets. So try and maybe sum this up for us. How should we assess this argument? Is this still a good argument for the recent origin of the solar system? It's been around in the creationist literature, as we've said, since at least the time of Whitcomb and Morris. And creationists will often use this argument and say, look, we have these comets that have these short lifetimes, much less than the conventional age of the solar system. But there's more to the argument than that these days, because we've got to deal with these kind of counter responses. So just try and sum up for us. Is this still an argument we should?
I think it's still a good argument. I use it in my classes at Bob Jones.
Yeah.
But we need to be more nuanced and mention, they've got these other ideas, and the observation evidence, the Oort clouds are kind of weak. And then the transfer mechanism is it seems more like hand waving to me, so.
Yeah.
it'd be great to get someone who really knows orbital mechanics, who's a creationist and is good at computer programming, to really start studying these out. They could get a bunch of papers published in the regular literature on this, but then they could point out in our journals, especially the quarterly.
Especially.
Yeah. Of course.
The implications of it.
Yeah. Yeah. So that's interesting. So the argument still seems to be a good argument, but we do need to kind of include these caveats that we have the Oort Cloud, we have these trans-Neptunian objects, the Edgeworth Kuiper Belt, and we need to address those in our argument. We need to kind of include those, but explain why we think they're not adequate to replenish the comet population.
I think that's really good. And then maybe this new one, maybe the Oort Cloud can't last long.
Yes, that's interesting. Yeah, that maybe the Oort Cloud itself has a limited lifetime. Mm-hmm. If it exists at all. We don't have...
If it was there.
If it's there. Yeah.
Yeah. I mean, that's kind of the essence of it feels very ad hoc, like we have to figure this out. So there must be something out there that's spitting comets into the inner solar system. That's just the end of the model.
Yeah. Now, this has been discussed a great deal in the creationist literature, and papers continue to be published on it. And we will put links to many of those papers in the show notes, so that people who want to sort of understand the nuances of this argument can follow that up. You've mentioned there the scope that there is for creationists to do more work in this area. And how can we encourage young students to consider astronomy, astrophysics as an area that they should study and go into? What are the opportunities that there are for students in these kinds of fields?
It's pretty well unlimited. It's just getting the vision for it. And I run into the same problem here. They have to be interested in that.
Yeah.
Yeah, there's a huge amount to be done, and we need more creation astronomers and astrophysicists, and like you say, those who can work on the orbital mechanics of these things and work out, how long the Oort Cloud can last, and whether the orbits of objects in the Oort Cloud can easily be transformed into short period comets, and there's all kinds of things that can be done. So this is one of the great things about creationism, actually, because we are so few in number. Any student kind of coming into this field, almost the world is their oyster. They can choose almost any number of fields, disciplines, sub areas, and there's something to do. And you can become something interesting, and they can become the creationist expert in this area because nobody else, has done that before. So I think this is really exciting. And I hope that there are some listeners out there, some viewers who are considering what they're going to go study at university. And maybe this is an area that they will choose to study because of this podcast. Wouldn't that be absolutely great? That would be something, wouldn't it? And I guess if they're interested in doing that, they can contact you, Bob. They can contact you, I guess, at Bob Jones University, or they can contact you via the Creation Research Society. Remind us how we find the Creation Research Society. You've got a website, presumably?
Oh, yeah. Just Creation Research Society. Put that in Google, you'll find it pretty quick. Yeah.
So do check that out. Do look them up. And we'll look forward to more papers on this subject in the quarterly, I'm sure. Thank you so much, Bob, for your time today and for the last episode too. It's been fascinating. It's been a great deep dive into comets. We've learned a great deal, and we hope our viewers have enjoyed it. I'm sure they will have done. We'll wrap things up for today. We don't know what's coming next. We always say that, don't we, Todd? But we will be back in 2 weeks with, I'm sure, something equally fascinating to talk to you all about. So we'll see you in a fortnight's time. We'll see you then.
See ya.
Thanks for listening to this episode of Let's Talk Creation. For more information, visit us at letstalkcreation.org, where you'll find an archive of past episodes and all our show notes. If you'd like to leave a comment or make a suggestion, you can find us on all the major social media platforms. Let's Talk Creation is brought to you in the U.S. by Core Academy of Science and in the U.K. by Biblical Creation Trust. As a listener-supported ministry, we are grateful for all of your financial support. Find out how you can make a contribution at our website, letstalkcreation.org. Also remember to like, subscribe, and share this episode with your friends. Thanks, and see you next time.